Hello and welcome. In this video, we're going to be talking about the ratio test for convergence for an infinite series. So let's go ahead and jump right in. As a little warm up here, I want you to look at each of these three geometric series and I want you to determine if they converge or diverge. So go ahead and pause the video and work through those three warm up problems. Then unpause the video and see how you did. So remember, all that we need in order to use the geometric series test is to be able to identify that we do in fact have a geometric series, what the absolute value of the ratio is, and whether that ratio is greater than or less than 1. So if it's greater than 1, like in example 1, that's going to diverge by the geometric series test. And if it's less than 1, like in both numbers 2 and numbers 3 here, then it's going to converge by the geometric series test. So let's think about a geometric series and the idea of a common ratio. A common ratio is what makes a geometric series a geometric series. So let's stop and ask ourselves some questions about what makes something geometric and see if we can extrapolate, if we can extend that idea to be able to come up with a test that works similarly to this test, but for a series that's maybe not geometric. So that's the idea in this lesson. So let's start with a few questions for ourselves. So how do we define the common ratio in general for a geometric series? Well, back in Algebra 1, you are supposed to learn that you can define a ratio as the term before divided by the term now. So if we had the series 2, 4, 8, 16, where our common ratio is 2, we could identify that ratio by taking any term and dividing it by the term before. 4 divided by 2 is 2. 16 divided by 8 is 2. So we can generalize that definition to say the ratio is a sub n plus 1 divided by a sub n, a term divided by the term before it. Now, every series can have this type of relationship between their terms. Every series can be discussed as having a ratio. The difference here is that a geometric series has a common ratio, and what we're discussing here is that that ratio may not be common. So every series can have a ratio between consecutive terms. That ratio may not always be common. If that ratio is common, then it's geometric. If it's not, doesn't it seem like there should be a way that we could still use the behavior of that ratio to come to some conclusions? So with a geometric series, we care about how the absolute value of our ratio relates to 1. And that gives us a lot of information about convergence or divergence as long as we can say what R is, and if it's greater than 1 or less than 1, we can conclude both convergence or divergence. Now take a look at this series here. This series at this moment is not a series we know how to talk about the convergence for. It doesn't diverge using the nth term test because n to the power of 10 moves slower than n factorial. So this limit would be 0. So we can't use the nth term test. It's not a P series. It's not geometric. I don't know what I would try and compare this to if I was going to use a comparison test. I don't know how to integrate with a factorial, and it's not alternating. So all of the tests that we have learned up to this point do not work for this series. So what I want you to do, or what we're going to do together, I should say, is let's think about the relationship between the next term and the term before. Let's think about the n plus 1th term and the nth term as a ratio. So what we're going to do is we're going to consider the limit as n goes to infinity of the ratio of the terms. And I'm acknowledging that that ratio is not the same. But what I want to see is what happens to that ratio as we go to infinity, because that's telling me a lot about the behavior of this series as we go to infinity. So let's go ahead and look at that limit. So the limit as n approaches infinity of a sub n plus 1 would be n plus 1 to the 10th over n plus 1 factorial. And if I'm dividing, that's the same thing as multiplying by the reciprocal. So I'm going to multiply this by n factorial over n to the 10th. So as we go to infinity, well, actually, regardless, n plus 1 factorial is the same thing as n plus 1 times n factorial. So these n factorials can divide out. So that leaves me with the limit as n approaches infinity of n plus 1 to the 10th over n plus 1 times n to the 10th. As we go to infinity, this denominator, if I distributed, would have a power of 11, and the numerator has a power of 10. So as we go to infinity, this limit is going to be equal to 0. So as we continue to add more and more and more terms together, what's happening to the terms is that they're going to 0. That ratio is becoming 0. What that means is that it's possible that this series could converge by a test that involves using the ratios. And that leads us to our ratio test. We're going to define that test, and then we can actually say that this series that we just considered is going to converge by the ratio test. So let's talk about the guidelines for the test and see what this test looks like. So the ratio test, again, because the idea comes from the geometric series test, the ratio test allows us to say if we look at the limit of the ratios as we go to infinity, and that ratio is less than 1, just like the geometric series test, we can say that the series will converge. If that ratio is greater than 1, or infinite, then we can say that that series will diverge. So this test for convergence, or this test, allows us to conclude both convergence and divergence. But if that limit is equal to 1, then we don't know anything. Right? We can't just have one test that works on everything. Otherwise, why do we have all these other tests? So the ratio test allows you to look at the behavior of the terms as they go to infinity. The absolute value just means that it doesn't matter if you think about the absolute value, it comes directly from the geometric series test. It doesn't matter if your terms are positive or negative. The ratio of them as they go to infinity is what needs to be considered. That's why there's absolute value there, because this is not affected if the terms have negative terms or positive terms. So let's go ahead and just practice using this test a few times, and then that's actually all that we're going to cover in this video today. So what we need to do is we need to consider the limit as n approaches infinity of the absolute value of, we're going to plug in n plus 1, so n plus 1 factorial, and we're going to multiply that by the reciprocal of the original term, or we're dividing by a sub n. So this is going to simplify to be the limit as n approaches infinity. 1 over n plus 1 factorial is the same thing as 1 over n plus 1 times n factorial. And I'm multiplying that by n factorial. So those n factorials are going to divide out. The limit as n goes to infinity of 1 over n plus 1 is 0. 0 is less than 1. Therefore, the sum from n equals 0 to infinity of 1 over n factorial is going to converge by the ratio test. Same thing for number 2. Let's consider the limit as n goes to infinity of, plug in n plus 1 and keep it the same. We can simplify this limit to be equal to the limit as n approaches infinity. The 3 to the n plus 1 and the 3 to the n's will divide out, so we'll be left with 3 in the numerator, and that n that was in the numerator of the red portion, over n plus 1. As we go to infinity, this limit is 3. 3 is greater than 1, so we can conclude that this series from n equals 1 to infinity of 3 to the n over n diverges by the ratio test. Now I want you to look at number 2. Is there another test for convergence or divergence that we could use on number 2 to draw conclusions? I'm hoping that you noticed that this series would also diverge by the nth term test, right? The limit as n goes to infinity of just 3 to the n over n is not going to be equal to 0. So based on just that fact alone, we can say this series would also diverge by the nth terms test. So don't forget all the different tests that we learned for convergence up to this point. Just because we're adding a new one to our repertoire doesn't mean that you can't use the old ones. So let's look at number 3. Go ahead and pause the video and take the limits on your own, and then unpause the video and see how you did. make sure you distribute that n plus 1. So the original will be the limit as n goes to infinity of the absolute value of 1 over the square root of 2n plus 2, because I'm distributing n plus 1 when I plug that in for n. This is going to become the limit as n approaches infinity of the absolute value, which is sort of unnecessary at this point, but of the square root of n over the square root of the square root of 2n over the square root of 2n plus 2. And that limit is going to be equal to 1. And this is the only time that the ratio test isn't going to tell us anything. So the ratio test is inconclusive here. So what I want you to ask yourself is, can you think of a different test that we have learned that would work to prove that this series converges or diverges? So hopefully you notice this is a p-series. This 2 being inside the radical doesn't change the fact that the denominator is a monomial. We could rewrite this, or the denominator is one term. I could rewrite that as 2n in parentheses to the power of 1/2. And by writing it that way, I can use the p-series test. P is less than 1. Therefore, this series would diverge by the p-series test. So always keep those things in mind, because even if this test that we just did, even if the ratio test was conclusive here, it would take much longer to look at these limits than it would to just identify what P is and draw our conclusions there. Okay, I'm going to give you 2 more examples that I'm going to encourage you to work through on your own, and then we're going to wrap up. Okay, here are 2 more series. Just by looking at them, it would be hard to use any of the tests that we know so far. The nth term test doesn't look like it would work here. It's not a p-series, it's not geometric. I don't know what we would compare it to. We don't know how to integrate here. So the ratio test does make logical sense to use on this series. So go ahead and perform the ratio test, consider that limit, and see if you can come to any conclusions using that test. And then unpause the video and see how you did. So here we are for number 4. If we take the limit as n approaches infinity of the absolute value of 4 to the n plus 1 over 2 times n plus 1 minus 1 factorial times the reciprocal of the original term, so 2n minus 1 factorial over 4 to the n. So if we simplified this, if I distributed here, this is 2n plus 2 minus 1, so that's going to be 2n plus 1 factorial. But since I want some terms to simplify, I can write that as 2n plus 1 times 2n minus 1 factorial, so that those factorial terms will divide out. This becomes 4 over 4n, or 4 over stuff with n. The limit as we go to infinity of that is going to be equal to 0, which is less than 1. Therefore, the series is going to converge by the ratio test. All right, let's look at the very last problem. So here's the setup for the limit. 5 to the n and this 5 to the n down here will simplify. 4 to the n and this 4 to the n will simplify, because again, as we go to infinity, the behavior isn't changing so dramatically. So we're left with, in the numerator, 4 and n plus 1, and in the denominator, 5 and n, and this limit as we go to infinity is just going to be 4 over 5, since the degree of the numerator and the denominator are the same. 4 over 5 is less than 1, so we can say that the sum from n equals 1 to infinity of n times 4 over 5 to the power of n will converge by the ratio test. So big idea in this section was talking about how we can extend the idea of using a ratio, even though we started with that idea geometrically, that we can think about the ratio of any series by dividing a sub n plus 1 divided by a sub n. And we can use that to come up with the ratio test and look at the limit as n approaches infinity of the absolute value of that ratio. If the absolute value of that ratio is less than 1, the series will converge. If it's greater than 1, the series will diverge. And if it equals 1, there's a different test that you probably should have used anyways before we get here. So just because we learned this new test doesn't mean that you should automatically jump to that test first. Don't forget, it was the very last test on the list of tests that we have covered. So remember all of the tests that we learned before this point, but this is just another tool to add to your tool chest. It's a great tool to use when you see a factorial or an exponential function that you're not sure what else to do with. So write down any questions you have, and I look forward to supporting you on this. Thanks for listening.